and we are back with the second solution to the 2016 AIME 1 problem number 11. So this is the second, more intuitive way to solve this problem, which is actually my favorite polynomial problem. So let's get started. I have just underlined the same information that we underlined in the last video, which was the first solution. So I'm going to reread the problem. Let p of x be a non-zero polynomial, such that x minus 1 times p of x plus 1 is equal to x plus 2 times p of x for every real x, and p of 2 squared is equal to p of 3. Then we want to find p of 7 halves, make sure the numerator and denominator are relatively prime, and then add the numerator with the denominator. Okay, so I don't know about you, but when I first saw this problem really, I really wanted to somehow use this blue highlighted identity here. Well, this is just the only concrete piece of information we have that really doesn't have any variables in it. And this does look like a really good starting point. So what can we do? Well, once again, we are going to try to find p of x. And the first thing we're going to do is we're also going to substitute values, but this time I'm going to substitute x equals 2. Why 2? Well, on the left side, we will have p of 3. And on the right side, we'll have something times p of 2. And both p of 3 and p of 2 appear in our blue highlighted identity. So what we get is the following. So, let's see. When x is equal to 2, we have that 1 times p of 3 is equal to 4 times p of 2. So, this leads to p of 3, which is equal to, by our blue highlighted identity, p of 2 squared. But on the other hand, this is equal to 4 times p of 2. So what does this yield? This yields that p of 2 is equal to 4. And therefore, p of 3 is equal to 16. Okay, this worked once. Maybe it'll work again. And now I'm going to derive a whole bunch of polynomial identities. So, let's see. So this is when x equals 4. We have this going right here. This was actually the first thing that I derived, like when I was first solving this problem. Then I realized that I can actually first derive it when x equals 3. And eventually we get that p of 4 is equal to 40. And I guess this is just a combination of this green identity and the two identities we derived earlier. And now we can use this to find p of 5 with this green identity. So this yields 80. And we just keep going, deriving a whole set of polynomial identities. So this is p of 6 is equal to 140. And we're going to derive one last one. When x equals 6, we have 5 times p of 7 is equal to 8 times p of 6, yielding p of 7 is equal to 224. Okay, so we just derived a whole bunch of polynomial identities. So let's just write out all of the values of p of x from 2 to 7. So 4, 16, 40, 80, 140, 224. Now, why are we doing that? Well, if you think back, I don't know if you remember this method, but in case you don't remember, I'm going to go through it. So assume we are given an example polynomial, not related to the polynomial we are working with in the problem. That is p of 1 equals 1, p of 2 equals 2, p of 3 equals 4, and p of 4 equals 7. Okay, and the problem is to find the degree of the polynomial. So how do we find the degree of this polynomial? Well, we take the difference between consecutive values of p of x, and then we take it again. And when we see a repetition, in this case 1 and 1, we count the steps it took us to get there. In this case, 1 and 2. And actually, we don't count the listing out of the values as a step. So we just go 1 and 2. And if the polynomial is a kth degree polynomial, then it always takes k steps to get there. And the opposite is true. So in this case, it took us 2 steps to get there, which means that the degree of p of x is equal to 2. Okay, so we have that going right there. Let's apply the same process here. We take the differences. This is 12, 24, 40, 60, 84. And now we take the differences again. 24, 20, 16, 12. Still no repetition, but hopefully it will be soon. 4, 4, and 4. Okay, that's a clear repetition. Let's mark it. So let's count the steps. 1, 2, 3. What does that tell us? That tells us that the degree of p of x is equal to 3. So p of x is actually a cubic. So let's write that down. P of x is equal to ax cubed plus bx squared plus cx plus d. Okay? So how do we use that? Well, this is a really common technique to find the coefficients of the polynomial. We just plug in x values. So what do I mean? Well, 4 equals p of 2. But on the other hand, with our above definition, it's equal to 8a plus 4b plus 2c plus d. And we do the same thing with p of 3, right? 16 is equal to p of 3, but that's also equal to 27a plus 9b plus 3c plus d by plugging in 3 into our expression for p of x. And then we do the same thing with p of 4. Okay. And we don't actually have to do this with every single value, because this listing out of equations will actually work for any 3 values that we choose here. So we're just going to choose the smallest ones. And I'm not going to solve this equation here, but I'm just going to tell you that this equation has solutions a equals 2/3, b equals 0, c equals negative 2/3, and d equals 0. I mean, I think on the test you should really have no problem solving this if you did get into AIME. So now we just have our polynomial. And like the last solution, we found our polynomial. It is 2/3 x cubed plus 0 x squared, so just plus 0, minus 2/3 x plus 0. And that is p of x. Now, how does this compare with the result we derived in the previous solution? Well, really, it's the same thing. Because we could just factor a 2/3 and then an x, and then we'll have 2/3 x times x squared minus 1, which is the same thing as 2/3 times x minus 1 times x plus 1, which is exactly the thing that we got in the previous solution. So that checks out. So now we found our polynomial. Let's just find p of 7/2. So we have p of 7/2 is equal to 2/3 times 343 over 2 cubed. I noticed didn't write out 8 because there's some cancellation going. Minus 2/3 times 7/2. After a lot of cancellation and some basic fraction arithmetic, we get that p of 7/2 is equal to 315/12, which is the same as 105/4. So as in the previous solution, this is our m, this is our n. We add them together to get 109. Okay, so I hope you liked this much more intuitive solution. I mean, I think that the previous solution was much more beautiful, of course, but this one is also a really cool solution. If you want, you can post in the comments which one you liked more, and I'll see you in the next video.